Okay, lecture starts. Again, it continues to be everyone's favorite time of the year, continues to be subject to evaluation time. Please fill out these evaluations. We read them, we use them. We appreciate you filling them out. 6033 in the news, continuing to focus on the colonial pipeline. The hackers have apologized and are promising to target less controversial targets in the future. And the thing that I thought was interesting about this, how would an adversary, or really anyone, think about what systems were sort of controversial targets? And I think part of what has come out of this is that, by attacking this pipeline, it has affected so many people, right? And I think that that is maybe in some ways a surprise, right? Like we don't always think about what people are going to be impacted by some, whether it's an attack or whether it's just a system failure, right? Like a machine crashes, right? So I just saw the saga of the Colonial Pipeline has just really consumed my news consumption for the past couple of weeks and is highly relevant to 033. All right, so today we're still in the world of security. And in fact, we are still in the world of attackers on a network. They're going to get bigger today, right? So let's see what we've been doing. So all of last week, we were focused on network adversaries. And so we started with secure channels, right? We thought about an adversary that was trying to observe packets, maybe do some tampering with the packets, like inserting packets or changing them in some way. And what we did here was create a secure channel, right? So the secure channel provides the confidentiality and integrity. That's what it means to be a secure channel. You get those two things. We saw abstractions like symmetric keys and MACs. We talked about Diffie-Hellman key exchange. Then we turned to public key cryptography and digital signatures. So on Wednesday, we kept our adversary in the network, but the adversary was still basically trying to observe packets and draw conclusions from those observations, right? Who was communicating with whom is sort of what we're looking for toward. So today, we're going to focus on adversaries in the network still, but they have a different goal, right? Their goal here of these adversaries, they're trying to prevent legitimate access to some online resource, right? These adversaries, they're not particularly interested in observing packet contents, right? So a secure channel is not something that is going to be helpful here at all. And we're going to talk about a few different attacks in this lecture. We're also going to talk about what makes these attacks difficult to detect and prevent. So this is kind of a really, kind of like a thorny lecture. There's going to be a lot of really sophisticated attacks here that are difficult to deal with, but we'll talk about some solutions, right? So first, this goal of on the adversary side. What does it mean to prevent legitimate access to an internet resource, right? How might we do that? Suppose, for instance, suppose that our adversary wanted to bring down the root DNS servers, right? You've learned enough, you know enough about DNS to know what a problem that would be. So one of the ways that an attacker could try to do this would be to congest the service and bring it down, right? So we had our adversary just sending a lot of requests to that root server, to as many of the root servers as possible. The root server is going to spend all of its time processing and handling those requests instead of serving like actual legitimate requests from, say, all of us. And in fact, to make this work, an adversary usually doesn't even need to send like legitimate traffic. We could potentially just send junk data to the root server. That could be enough to overflow queues to prevent legitimate traffic from getting through, right? You all know how that works, right? On a network, lots of packets go in, queues fill up, packets get dropped, right? If an adversary is filling up all the queues and my packets are getting dropped, oh, that's bad for me, right? I no longer have access. So that type of attack, that style of attack where we're preventing access to a resource is known as a denial of service attack, or a DOS attack, so DOS. When it's mounted for multiple machines, it's known as a distributed denial of service attack, or a DDoS attack. So that is what we are going to look at today. Right? We're going to see adversaries targeting any resource maybe link bandwidth, maybe the routing system, maybe access to a database, all sorts of things, right? So the first question to ask ourselves is, well, is this really this bad, right? It used to be maybe 10, 15 years ago when you'd hear about DDoS attacks, they just tended, or the ones that you heard about tended to be on like specific websites. Like this website was brought down by a DDoS attack. You know, it would be down for a few hours, it would come back up after the attack was over, right? This might not seem like the end of the world, right? But these days, we use websites for really important things, right? If my bank's website is down, right, how am I supposed to transfer money, right? The example I gave at the beginning, if the root DNS servers are brought down, right, huge things could happen. You can even see DDoS attacks on infrastructure, right? Again, we've been looking at this in the news segments. We've been looking at this ransomware attack on the Colonial Pipeline, which is basically the adversaries sort of got into the system, encrypted some data, and are charging money for the decryption key. Right here, we have an example, and this is so 4 days ago. That's not 4 days ago from now. I want to say this was 2019 or 2018, where there was a DDoS attack that disrupted like the energy grid. Right, so we depend on the internet for so much of our commerce, of our lives. Successful DDoS attacks can be really, really bad. Right, so a solution you might imagine at this point is to sort of just like toughen up our network resources, right? Get more bandwidth, right? Something like that, right? How much traffic could an attacker with a few machines really generate? So let's talk about botnets. All right, I have that on the slide here, that the primary method our adversaries are going to use today is DDoS attacks, which they're going to make more effective with a botnet, right? So what is a botnet? That's what we're going to talk about first. You're going to talk about this way more in recitation tomorrow, but I'm going to give you some context today. All right, so our threat model, our adversary has a botnet. It's trying to prevent access to a legitimate service. We will talk more about the specific attacks in a second. What we want to do with the non-adversarial people in this situation do, we want to try to maintain availability of the service, right? If an adversary is trying to bring down Katrina's amazing web suite, I don't want that to happen. I want real people to still be able to use it, all right? But we need to understand our adversaries a little bit more, so we need to understand what they have at their disposal, and what they have at their disposal is a botnet. All right, so a botnet is a large collection of compromised machines that are controlled by an adversary. So when you're thinking large collection, 100,000 machines, right? That's a decent size, right? What might one do with a botnet? Well, you can mount DDoS attacks, among other things, right? So there are a couple of questions here. How could so many machines become compromised, right? How does the adversary control the machines? This feels like a lot of work to have to sort of compromise all of these machines and sort of build the botnet, right? Well, that last problem is kind of easy to solve, right? As like disappointing as it is. Not you in this class, one can rent a botnet, all right? So there are botnets out there. You can go and rent them. Do not go out and rent a botnet. I will not defend that decision. They are surprisingly cheap, all right? So an adversary can rent a botnet. So how does this botnet work? All right, well, first, we have a bunch of machines, right, that have been compromised. There are so many different ways the machines can be compromised, right? You've probably heard of things like worms, viruses, Trojans, all of these things. A common way for a machine, like say your laptop, like a user sort of machine, would be to visit a website that is vulnerable to something called a cross-site scripting attack. All right, so the high-level idea of how this would work is if you imagine a website that allows for user input. So something like comments on a blog, right? We're not doing a lot of blogging these days, but just imagine that, right? If an adversary shows up, they can comment on the blog and include like a script in it, right? Like an executable script, like JavaScript style code, right? And so if the system isn't checking for that, most systems these days are, but if the server is not checking for that, right, that adversary uploads their comment, and now when a user goes in, loads the page, that script will execute. It will execute as part of the comment, right? And if that script say, has the user download, in the background, some sort of malicious code. That is one vector of attack, one way to compromise a machine, right? You will find, you will learn about other ways to compromise machines in tomorrow's recitation, right? So you're gonna look at a particular botnet that works a bit differently than that idea. And there are basically lots of ways to compromise a machine. All right, so once the machine is compromised, it will sort of set about installing some code that tells it what to do as a bot. In some contexts, we'll call that a rootkit. All right, so this machine is not compromised, it is a bot. How does it get to be part of this network of bots, right? How does it join the botnet? Right, well, so botnets are typically organized in a hierarchy, right? So that rootkit that gets installed on bots, it will tell them to contact a command and control server. So the CNC server here. The paper for recitation tomorrow calls these C2 servers. So I have a couple of notes on this lecture slides that relate the content of lecture to tomorrow's paper, just so you know where things are coming up. Right, so the software that gets installed on these bots tells them how to contact the CNC server, how to respond to commands from the server. And the commands are literally things that look like this. There are things that say like DOS this IP address, right? Which basically just tells the bots, send as much traffic as you can to this IP address. It can be nonsense traffic. It can be junk traffic, right? These bots aren't concerned with actually getting a response. They just want to clog things, right? So there are all sorts of things that you can do with a botnet. I really like this image. I got it from Wikipedia. I think it's pretty funny. This is not a bad description of how a botnet works, right? So you can see our adversary up here at the top. It gets a Trojan of some sort onto the machines. The machines then sort of say like, okay, we're here, we're ready. Another adversary shows up, rents the botnet. And then people are overwhelmed with spam, right? So spam is something that one can do with a botnet. We're going to focus mostly on DDoS style of attacks, so not sending spam. And before I give you some of the specific ways to mount these attacks, I actually want to first start thinking about how might we prevent them, right? Because at this stage, knowing what you know now, there are a few ways, or there are a few things that seem like they should be things that we should do to prevent this, right? So one might just be, can we just block the IP addresses of all of the machines in the botnet, right? Like if I see IP address like 2.3.4.5 is sending me a lot of junk traffic, can I not just somewhere in the network block that traffic, right? That's not a bad idea. But as it turns out, IP addresses are really easy to lie about. They're easy to spoof, right? So bots can change their IP addresses rapidly, right? So that style of blocking, it's not going to be super effective. It's not going to scale super well, right? And again, remember, these bots are not concerned with getting responses back, right? Normally, I don't want to lie about my IP address because I want a response from whomever I'm communicating with. But I don't care about getting a response. It doesn't really matter what source address I give, right? So that's not totally going to work for us. So we can think about, well, okay, instead of preventing our attacks, can we just build better systems, right? Can we distribute our systems so that a DDoS attack doesn't bring down the entire thing, right? That's a good idea. In fact, we haven't talked about it yet because it didn't come up until today. Among the reasons for not building centralized systems is fault tolerance specifically against DDoS attacks, right? We think about, okay, centralized components are this centralized source of failure, right? A single point of failure. One of the things that can cause them to fail is an attack like this, right? So thinking about how to distribute systems so that they are resilient to these attacks is a great idea. But you have seen from this class, you can't just snap your fingers and get that, right? Distributing a system can be complicated. It's not always feasible, right? It might not be economically feasible to do that. You might not have enough money to buy enough machines, right? So if we think more back into the world of, trying to prevent these attacks, right? Even if we're thinking, well, okay, blocking IP addresses probably isn't going to work directly. But even if we were to pursue that, how would we figure out like which IPs are part of the botnet? right? We need some way to detect these attacks before we prevent them, right? So there are systems that are built to do this, among other things. And these systems are typically fall under the umbrella of network intrusion detection systems, sometimes called NIDS, so NIDS, all right? So we're gonna look at some approaches to detecting different types of network attacks. So it could be DDoS attacks, but this is actually a more general class of systems, right? So the first thing we'd have to think about is, okay, what are we even trying to detect, right? We could look for, I'll call it like an offending packet, right? Like we could observe our network and look for a packet that says like, hello, CNC server, like I'm a bot, I'm ready for service, right? That would be sort of a suspicious packet, right? So that's sort of one thing we could think about. It might not work in all cases, right? Bots could be encrypting data, right? Or something, but okay, there's this sort of idea of just looking for packets that seem suspicious. We could also look for some sort of like attack characteristics, right? If we see a lot of machines sending us traffic in sort of the same manner, right? Sending a lot of traffic all at once, right? We might get suspicious if they're all bots in a botnet, right? Those two approaches give rise to sort of what tend to be the two main approaches of these systems, right? Of these network intrusion detection systems, right? So that first idea where we're looking for like a suspicious packet of some sort, that is known as a signature-based approach. And so we have a signature-based NIDS. We're keeping a database of known attack signatures and matching traffic against that database. So I'm going to show you an example of a signature just so you have a sense of what I'm talking about. I'm not expecting you to learn the signature syntax because it's very weird and it's specific to specific systems, but it might look something like this, right? So what you're seeing here at the beginning, so this is looking for TCP traffic coming from some external network on any port. Traffic is coming into our home network on a specific port, 7597, right? And then all sorts of other things about, you know, potentially some text that might be in the packet, just some other rules about what this traffic looks like, some metadata about this traffic, right? So this is an example of a style of signature. So it's not saying just look for this string in this packet, but it's sort of looking for these well-defined characteristics, right? It is easy to tell if a packet is TCP traffic coming in on port 7597. Like that's quite a quick and easy check to do. So there are some really great things about this approach. One is that assuming you work with these systems, it's relatively easy to understand the outcome, right? So what I mean by that is like, if traffic matches this signature, it will be blocked or processed or dealt with in some special way. And it can be really accurate in detecting known attacks, right? Like if this particular, say, worm or virus or whatever always comes in on port 7597, well, we can do a really great job probably of blocking that traffic, right? But then the negatives to this approach are just the things that are sort of the opposite, right? This approach makes it impossible on its own to discover new attacks, right? And also, we don't, you know, as a community, we can't really develop these signatures until we've seen the attack at least once, right? And hey, once might be enough for our adversary, right? So that, you know, those things aren't great. So contrasting this, you have these anomaly-based systems. So these match traffic against a model of normal traffic and then flag abnormalities. And they sort of, in some ways, they are like the dual of the signature-based approach. These systems can potentially deal with new attacks, right? But the downside is, well, okay, how do we model normal traffic, right? It's hard to describe what's normal. Whatever model we use potentially limits like the growth of new applications on our network, right? Like new, totally benign, maybe even positive applications, like non-adversarial applications, because they'd have to fit this model of normal traffic. Otherwise, they'll be classified as anomalous, right? And then sometimes this approach can have a less accurate detection of known attacks. And so most systems, they take a hybrid approach. They'll match against a database of known attacks. If there's no match, they'll check for an anomaly. So there are lots of these sort of systems out there. And the majority of these systems, again, they're not just detecting different types of DDoS attacks. They detect all sorts of things going on in a network. And they typically give users the ability to, like once an attack is detected, try to do something about it, right? Try to prevent it in some way, right? So that is not out of the scope of this lecture, but just so you understand what they do, right? So we're not going to go too in depth into exactly how these systems work. And the reason we're not going to go too in depth into it is because they are quite complicated, right? The theme of this lecture, like the sub theme of this lecture is sort of network attacks are difficult to detect, right? And they're difficult to prevent. What I want to show you, I want to give you a sense of just how difficult this can be. Not impossible, just challenging, right? Because here's what we're going to do. We're going to think of like just a really simple style of attack, right? Imagine we're trying to detect a botnet, and as part of that botnet communication, we know that we're going to see a packet, or like we're going to see the word root just somewhere in the string, right? Like it's a login with like user root or something like that. So let's think about how we could detect that, right? You know, we could just say, okay, for each packet that comes in, search it for the string root. And if we see it, you know, do something, right? We'll kind of ignore exactly what we're going to do for now, but this is what we're looking for, right? Well, you know, the string might be split across packets, right? I send R in one packet and then O in the next packet. I'm the adversary here, and O in the next and then T in the next. So, okay, we're all computer scientists, right? We can deal with this. We'll sort of try to, you know, we'll remember previous packets, right? Construct a stream of data, right? Well, that's not too terrible, but packets might arrive out of order, right? I've got sequence numbers. I can rearrange all sorts of things as the adversary, right? So we'll say, okay, fine. We're gonna like fully reassemble the byte stream, right? All of the data. Totally possible if, you know, our adversary is using TCP, right? We can do this, all right? This is a little bit more difficult than it looks on the slide. Obviously not impossible. Your computer is reassembling TCP byte streams all the time. It requires keeping a decent amount of state, right? But it's not impossible, right? The lingering problem with this, though, is that the adversary, can still evade it, right? So let me show you one way that I might evade what is, you know, ultimately a thing that seemed like it was going to work pretty well. Right? We're just looking for the string root, right? So here's our setup, right? So what do I have going here? I have 3 machines. There's the adversary, which today is me, not Howie, right? Some receiver, which is the person that I'm trying to, you know, maybe attack in some way, or that's the CNC server that I'm communicating with, whatever. I'm trying to get traffic there. And then I have my network intrusion detection system. Right? So typically when you deploy these systems, they sit maybe at kind of the edge of a local network, right? So you might imagine owning a company, you've got your internal network, all of your machines together, your network intrusion detection system sits on the edge of that network. All right, so the way that I've illustrated this in this slide is, okay, there's going to be a bunch of hops between the adversary and the network intrusion detection system. And then there's still going to be a few more hops until the receiver. This is a very normal setup. The numbers 15 and 5, they're not special. They could be whatever numbers. I'm using 15 and 5 here. All right, so what does this matter? Let's see what the adversary might do. All right, remember what I'm trying to do here. I'm trying to kind of confuse this system. I'm trying to evade its detection mechanisms, right? So here's the first packet that I'm going to send. All right, it has a sequence number of 1. It contains the letter R. So this here is the data. That's the only data I have in this packet. The other thing, though, that I have emphasized here is the TTL. TTL is the time to live field. What the time to live field in a packet does is says this packet can travel this many hops through the network. In this case, it's 23. So this packets travel through the network. that TTL gets decremented at every switch. If it reaches 0, the packet is dropped. The reason we put a TTL field on packets, among a few other reasons, one big one is though, if something weird happens in the network, such that there is like a routing loop for a little bit of time, the TTL stops us from just sending packets around and around and around in a circle forever, because they'll get dropped once the TTL expires, right? So this TTL though, there's something really weird about this packet. Notice 20 hops from the adversary to the receiver. This packet is allowed to travel 23 hops. It's gonna get to the receiver, right? Well then, maybe I send this next packet though with a shorter TTL, right? This packet now is going to be received by the intrusion detection system, which is only 15 hops away. It's not going to be received by the receiver. So what does this do to me? Well, this means that if my intrusion detection system is trying to deal with state, it's got some things to think about. Right, sequence number 1, it saw 2 copies of that packet and the data was different. So as it's trying to think about reconstructing the data, this is now a little bit more challenging. Right, on the receiving side, receiver's not confused. Receiver only got 1 packet. Right, so I can keep doing this. Right, I'm varying the TTLs a little bit here. Sometimes I'm only sending 1 packet. Again, these numbers aren't special. They're just the numbers I picked for this example. Right. So what you can see in this style of evasion, I'm confusing the intrusion detection system, right? It's having to keep a lot of state, right? It's trying to figure things out, right? Now, again, in this case, our intrusion detection system, it can get smarter. It can say something like, well, if I see, 2 copies of the same sequence number, I'll keep the one with the higher TTL or something like that, right? They can certainly evolve to deal with these styles of evasion, right? But it gets more and more and more complex, right? And it involves keeping more and more and more state, right? Another way that adversaries might try to evade detection in these styles of systems is to try to mount an attack on the detection mechanism itself. Many of these systems do detection in real time, right, instead of offline, because real-time detection can help in throttling the attack as it happens, right? But if the adversary can attack the detection system, that can cause problems, right? So the thing that I wanted you to take away, it's not that these systems are impossible to build. They're not impossible to build, but they're difficult to build. Even attacks that seemed as though they might be easy to detect, right? Searching for a particular string in a sequence of data, they can get a lot more complicated. They're relatively easy to evade by adversaries, right? So instead of solving this problem, I'm going to make our lives even more difficult, right? I'm going to make our lives more difficult by showing you some attacks that mimic legitimate traffic, right? Which makes them even more difficult to detect, right? Like you might look at this sequence of packets and say, this is iffy. Something weird's happening here, right? Or maybe you wouldn't. We're going to look at attacks that just get more and more legitimate, all right? So these attacks are interesting because they are not necessarily trying to exhaust the set of resources that we normally think about with DDoS attacks. All right, so the way I've sort of presented these attacks to you is like, well, the bots are going to send a ton of traffic, right? That's going to fill up queues around, the server, the machines they're targeting. It's going to prevent, other legitimate traffic from getting through. That's certainly one style of attack, but there are some others, right? So I am going to show you 4 of them, going from my least favorite to my favorite, which is fun for me. All right, so here is a person. They run a web server. All right, here is our adversary, and I'm only drawing the adversary as one little icon here. Remember, we have a botnet. Okay, so it's a lot. It's big. It's a big adversary. All right, so an attacker might show up and say, your web server, it can do a lot of things. It serves HTTP requests. It can do some database queries. Right? Those are all normal things for a server to do. So maybe this adversary shows up and says, hey, I want to download this really big file, right? Which is a file that you're hosting. You get requests to download this file on occasion, right? Nothing weird about this request on its own. But you get a little bit nervous, as indicated by the emoji here, because it involves a lot of computation, a lot of data going out of your machine, right? Well, alongside this, and remember, the adversary does not actually care about getting this file. They don't need it. They also ask the survey, hey, can you also do this query? Right? Can you run this really computationally intensive database operation, right? Maybe it's searching through a particular database or something like that. And, bots in a botnet could send quite a lot of these things at once, all right? So what you can see is that your server, this person's server, is going to spend much of its, database resources, its disk bandwidth resources, serving these requests, right? And any one of these requests on its own, it looks totally legitimate, right? It just happens that they're getting a lot of them at once, right? So this is one style of attack we might see. In the Mariah paper for tomorrow's presentation, this is similar to the HTTP flood attack that they mentioned in that paper, right? So this is attack number one, right? Which again, exhausts resources on the server more than it exhausts the network around the server, right? Second attack deals with TCP. So if you felt like a lack of TCP in your life since, March or whatever, today's the day for you. Right. So first we have to talk about a normal TCP thing. This is not an attack. This happens all the time. To start a TCP connection, there is what we call a handshake. Right. There was a handshake in TLS. We looked at that with the secure channels lecture. It's a part of a protocol that gets things set up. Right. So the TCP handshake looks like this. Right. The person initiating the connection sends what we call a SYN packet for synchronize. So a SYN packet. The receiver stores some state. It's not like a ton of state. It's, hey, I got a TCP connection from this IP address on this port. This is maybe the version of TCP we're using. This is the starting sequence number, things like that. They respond, right? They ACK the SYN packet, and it also has some synchronization information of their own. So we talk about this as the SYN-ACK. And then sender also stores state, and they send this final ACK. So we might hear people talk about the throughway handshake for TCP, SYN, SYN-ACK, ACK. I don't know if Hari's on Zoom. Hari used to have a cool t-shirt about this process. So this is normal. This happens in every single TCP connection all the time. Here is an abnormal part. Oh my gosh, Broccoli just sneezed and scared me to death. What are you doing? You're disrupting the lecture. Okay, now we have an adversary here, all right? So you can tell things are gonna get bad. Oh, Broccoli's coming over to disrupt the lecture even more. Cool. All right, so here, our attacker sends a SYN packet. It's a totally normal looking packet. Your computer gets a ton of these packets every day. All right, so our victim here stores the state that they would normally stir, and they send the SYN-ACK back. I have this grayed out because this adversary is not actually interested in connecting, right? But maybe our victim's getting a little bit worried. They're starting to exhaust some resources, but it's not that much state. It's fine. The thing is that the attacker is going to keep doing this. They're going to send a ton of SYN packets, right? And even this is not terribly suspicious. You might have multiple TCP connections open between you and like a particular IP address at the same time. But eventually our adversary can keep doing this. These SYN packets are so small, they're so easy to send. They could totally exhaust the state on the victim server. Now, I've only drawn 4 SYN packets here. You would need more than 4. Okay, 4 is not actually gonna do it. But this is a relatively easy attack to mount. And again, it's not about exhausting the network. It's about exhausting the state on the server, right? This one does have a bit of a fix for it. So TCP will time out on connections that are half open. So connections where like the victim's machine has received the SYN and sent the SYN-ACK, but not finished the handshake. I want to say it times out after like 2 minutes, but I might be wrong about that exact number, right? But still, even within 2 minutes, you could try to do a lot, right? Third attack, right? Also on TCP. And again, we're going to start with just normal TCP. So what I'm about to show you, nothing wrong with this. right? This is just to remind us what ACKs look like at the beginning of a TCP connection, right? The beginning of the TCP connection, we're doing slow start. I send a sequence number, I get an ACK back. Once I get the ACK back, I'm gonna double the size of my window. I'm gonna get 2 ACKs back, and double the size of my window again, right? This is slow start, right? We're doubling every round trip time. Nothing bad here, right? One of the things though, that you might have picked up on when we were talking about TCP, this, reception of an ACK in TCP also starts to tell you something about how much data can get through the network, right? When I get an ACK, it indicates that a packet has left the network, there's room for another network. So they sort of pace us correctly, right? And slow start is different, we're getting exponentially bigger, but in steady state, they'll help pace us. So in this attack, our adversary is gonna exploit that a bit. So I've got, I'm sending a sequence number, sending some data to this adversary, right? Instead of responding with an ACK as soon as the adversary receives a packet, it's going to be optimistic, right? So this is known as optimistic ACKs or opt-ACKs. It's going to send the ACK soon, right? It's just that before it actually gets the packet. Remember, the adversary could not care less about reliable transport, right? It's just trying to do bad things. It's going to ACK packets whether it's gotten them or not, right? So our person on the left here was not really expecting to get an ACK, until there. They've gotten one earlier. So they're going to start increasing their window. And these ACKs are going to continue to come too early, right? What this means for our victim here, they're putting data into the network too fast, right? They're in some sense DOSing themselves, right? They're sending data out on their outgoing link more than it can actually handle, right? Because that adversary is just saying, send more. Because again, it doesn't care if packets get dropped, right? It's an adversary, right? So this is an optimistic attack, right? And these TCP attacks, they can be mounted against any machine that is using TCP, right? Web servers, FTP servers, all sorts of things, right? Like, don't just think about, victims in these scenarios as being individual users. Any computer, right? So now that is attack number 3. Now we come to the 4th attack, my favorite way to mount a DDoS attack, which again, you all are not going to go out and do. All right, so here is what it looks like. Here's the setup. All right, so we have our victim here. They have a particular IP address, which I need for this example. We're going to use 1234. It doesn't matter what the IP address is, like any IP address will work. We have our adversary here at the top. Remember, our adversary is really a botnet. And we have lots of DNS name servers at our disposal, right? We all always have a lot of DNS name servers at our disposal. Everybody can send messages to DNS name servers, okay? It's even better for us if these DNS name servers are DNSSEC enabled, which might be surprising, right? It is better for our adversary if these name servers use DNSSEC, right? Which is wild. The point of DNSSEC was to try to be more secure, right? This is because our adversaries are taking a different style of attack than what DNSSEC is trying to prevent, right? So my adversary here is going to send some DNS requests to these name servers. So they are very, very, they are correctly formatted DNS requests. There is nothing wrong with the requests themselves, but there are 2 things that are special about them. One is that as an adversary, I'm gonna spoof the source. I'm gonna lie about the source address, right? I'm gonna put in these packets that the source is 1234, right? What this means is that the responses to those requests, they'll go to whatever the source address was. So they're gonna go to 1234, right? And then the second thing that's special, the reason that I wanted these name servers to be DNSSEC enabled, is I'm gonna request some relevant information related to that protocol. Maybe, for instance, a DNS key record. The reason I'm going to do that, those responses tend to be very large, right? Especially large compared to the size of the request, right? So I only have to send a little bit of data to make this request. In response, I get quite a bit of data, right? All these DNS key options and things, right? So what this means, all of those responses, all of those larger responses, those amplified responses, they go straight to our victim, right? So this is known as a DNS amplification attack. You'll sometimes also hear DNS reflection attack. Amplification implies that we get more traffic sent through this attack than we actually have to send to initiate it, right? And think about how we might prevent this, right? Here, the traffic to the victim's machine, it's not coming from the botnet. It's coming from these machines, right? It's coming from these DNS name servers. We might, in normal times, like want responses from those name servers, right? You can imagine things like, the victim ignoring DNS responses from name servers to whom it has not made a request recently, right? Ignoring the response though, like on your machine, doesn't prevent the response from getting to your machine, right? From filling up the queues sort of near your machine, right? So this is a complicated style of attack to defend against. To kind of finish this up, there's one other type of attack that is sometimes just kind of comes in the realm of DDoS attacks. It's not quite the same. Imagine our adversary gains access to a switch, right? What could it do? Right. It could do a couple of things. It could overload like the CPU on the switch with a bunch of routing changes. So it's doing a lot of computation about recalculating routes. It could try to like overload the routing table with too many routes. So there's a couple of local things it could do on the switch. One of the maybe more concerning things though that it might do is if you imagine a switch involved in BGP, right? You remember BGP. Here we have ASs announcing things about like what destinations they can get to, and in particular, what destinations they own, right? So part of the BGP announcements say that like, I am this AS and I have these IP addresses sort of in this AS, right? So if you want to send to those IP prefixes, send them to me, right? Or something like that. If an adversary gets access to one of those switches, it could just lie. It can lie about BGP, right? I told you this when we did BGP, that BGP is basically on the honor system, right? An adversary can lie and say they own a prefix that they don't, right? The consequences of this, packets are going to go to a part of the network where they don't belong, right? Maybe they just get dropped. That would be like almost the best case. They could be used in some way. So there was an attack a couple of years ago where adversaries used this scheme known as prefix hijacking to steal Bitcoin from people, so like to steal actual money. One of the most famous instances of this was, this has been quite a while ago now, all of YouTube traffic was directed to the wrong country. So nobody could use YouTube for quite a while. In some ways, I mean, this isn't really a DDoS attack, right? In that example, YouTube was not like brought down by congestion. It actually pulled traffic away from YouTube. But there are lots of things that can go wrong if you have adversaries like this in your network, right? And just like you've seen with DNSSEC, there are proposals to secure BGP, to secure these style of protocols. They're slow. They take time to get adopted by everyone, all right? So what are you going to take away from this like frightening and potentially depressing lecture? All right, so one is that this style of attack is important to understand, right? There are things that adversaries can do that is more than just sniffing your traffic and trying to read your data, right? They can try to prevent access to a particular resource, and those resources these days are very important, right? They involve real people and real money and real things that we need to survive, right? There are ways to prevent these attacks. There are these network intrusion detection systems. They're not perfect, but they can work well. They are complicated though. These attacks are maybe easier to evade than you would expect. The other thing though that you should take away from the class, right, is that we can build systems that are more resilient to these types of attacks, right? Again, another reason to have distributed systems is to make these sorts of attacks more difficult to mount, right? That is not a straightforward process, right? We did like a whole class on it, right? But that is one of the other defenses that we have here. So for instance, we talked about, when we talked about DNS, the root zone of DNS is hundreds of physical machines, right? Distributed because, you know, random failures can happen, but also targeted failures can happen, right? So this is it for network adversaries. This is the second to last lecture. On Wednesday's lecture, we're going to do something fun, as we do in every lecture, but it's going to be especially fun on Wednesday. We're kind of going to wrap some things up. So this is largely the end of the technical content related to security, but Wednesday's lecture will be pretty fun. If requested, I will show you Broccoli on Wednesday, and I'll bring a little hat for him to wear, which is generally a crowd pleaser. So you get 4 minutes early today, but I will happily stick around if there are questions.